Welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem cow checkups. This was the third problem from the January 2025 USACO contest in bronze. So the problem summary is that we are given two arrays, one called A, one called B, and our goal is to determine how frequently AI is equal to BI after reversing the array A from position L to position R. And the twist here is that we have to do this for all possible choices of the values L and R. So this problem was strange for many reasons. One, it was difficult, if not impossible, to get full credit on the question in Python. If you guys have a full credit Python solution, I would love to see it. Um, and then if you were coding in a different language, this was just a brute force problem. So as long as you brute forced over the arrays in the correct order, no sort of clever tricks were needed here. Brute force was enough to get full credit. So let's take a look at the naive brute force algorithm. So this is a good way to get partial credit on the problem, and then we're going to talk about how we can make it a little bit faster. So in the naive algorithm, what do you want to do? You just want to loop over all choices for L, loop over all choices for R, reverse the array A, and then loop over the array and count how many times AI is equal to BI. So let's write this out just so we can see. So loop over all choices for L, loop over all choices for R, and then we are going to reverse A from L to R, and then we are going to loop over the array and then count if AI is equal to BI, we'll increase some counter by 1, and then we will save frequency of the count. So to do this, we can create a frequency array for all possible counts. Um, and then this would be initialized to all zeros. And then when we see one particular count, we can just go to frequency and increase the frequency array of that particular count by 1. So this is a pretty straightforward algorithm. It should be sort of your first idea when you're approaching a question like this. But you want to analyze the runtime. And what is the runtime of this problem? Well, we can see we've got sort of 4 loops, 3 of them nested. So reversing A from L to R is a loop, but it's going to be sort of the same runtime as this loop. So we're just going to count these 3 loops, a loop over L, a loop over R, and a loop over the arrays. So each of these loops is approximately the length of the array. So if we call n the length of the array, the runtime here is going to be roughly n cubed. And in the problem statement, the maximum value of n was 7,500. So the total runtime is going to be roughly 7,500 cubed, which is going to be a large number. So this is going to be too slow. So what we actually want, sort of our goal, our objective, is to find an algorithm with runtime n squared. And so what can we afford to eliminate from this algorithm? Well, not a whole lot, right? Because we have to calculate the count for every choice of L and every choice of R, then it doesn't really seem like we can eliminate these 2 loops. We have to have one loop looping over all the possible choices for L and one loop looping over all the possible choices for R. That means what we have to do is eliminate a loop where we sort of loop over all the elements between L and R, reversing the array. And we also have to eliminate this loop over the array, counting if the elements are equal or not. So what we want to do here is sort of a mixture of pre-computation. So we want to sort of pre-compute initially how many elements in the array are equal. And then we want to cleverly loop over all of the different choices for L and R so that we don't have to repeat this work of reversing the array over and over. Because right now, if we're just looping over pairs of L and R as follows, let's say we like loop over 0, 0, we reverse that. Then we loop over 0, 1, we reverse that. We loop over 0, 2, we reverse that. Loop over 0, 3, we reverse that. We're going to end up doing a lot of repeated work. And the idea here is let's write out a large integer array, and I'm just going to use the values from 0 to 9. And let's say we're focusing on this point 4, and I want to reverse all of the values where 4 is the middle of L and R. So this would be the pairs LR is equal to 3 comma 3. There would also be a pair LR is equal to 2 comma 4. So that would be this chunk of the array. There's also a pair where LR is 1 comma 5. So that would be this part of the array. And if I do LR is equal to 0, 6, this is the final one here. We can see, again, all of these choices for L and R have this element as the central point. So if I were to make a sort of a naive choice for these loops, and I just did for L from 0 to n minus 1, for R from L to n minus 1, I would be looping over these different intervals at different times throughout my algorithm. So I couldn't reuse any information from like one interval in order to help me in the next interval. But maybe there is some way I can loop over these intervals all at the same time. And the benefit of looping over all of these intervals at the same time is they build on each other. So if I reverse everything from position 3 to 3, well, that does nothing. The interval stays the same. Then if I reverse everything from 2 to 4, I'm just going to swap the 5 and 3. And if I've already reversed everything from 2 to 4, now it becomes very easy to swap, to reverse everything from 1 to 5. If I want to reverse everything from 1 to 5, given that I've already reversed everything from 2 to 4, then all I have to do is swap these two elements. So I will swap the 6 and the 2, and now we can see that I've reversed everything from positions 1 to 5 in just a single swap. And the same thing holds true here. If I want to reverse everything from position 0 to 6, given that I've already reversed everything from position 1 to 5, then all I have to do is swap these two elements and I complete my reversal. So instead of having to restart my reversal from scratch each time, if I loop over the intervals in this particular order, then each reversal only takes one operation, one swap of elements. So my brute force algorithm should, instead of just looping over L and R in any sort of random way, I want to loop over all choices for like a middle element, and then I'm going to loop over all arrays that include that middle element. So algorithm idea, loop over all choices for a middle element, and then loop over all LR intervals which include the middle element. And now this reduces it to a n squared algorithm. The one thing to watch out for is you'll note that the size of these intervals is always going to be even, right? So this is a size 0 interval. or I guess if you're counting the number of elements, it would be odd. So this would be a size 1 interval, size 3 interval, size 5 interval, size 7 interval. There are even intervals as well. Um, in the case, to generate even intervals, we'd look at two middle elements. Um, so we will have to have sort of two separate cases. One where we loop over everything starting from a single element and expanding outwards, and one case where we start from a pair of elements and then expand outwards. Just to connect this to problems you may have seen in the past, this is the same algorithm you'd use if you want to count palindromes quickly. So if you've ever seen a question where someone has asked you to count the number of palindromes in a string, you can do that using this same idea. So this sort of shift of how we're looping over the string comes up in a lot of different problems, and it's always a good idea whenever you're coming up with a brute force algorithm to think about your choice of not just am I going to loop over these objects, but in what order am I going to loop over these objects, and is there some way I can loop over the objects in order to make this faster? So let's take a look at the code here. So my plan is we're going to start off with a C++ algorithm. So I'm going to go through the code in C++, but since I know a lot of people watching these videos also work with Python, I will show the equivalent Python solution at the end, even though that Python solution is too slow to receive full credit. So let's start off here by just initializing all of our variables. So we are going to read in a value n, and then we're going to create two arrays, a and b, and then read in all of the values of a and b. In order to eliminate this loop over the array where I'm recounting the number of elements that are equal, my very first step is going to be a step of pre-computation. I'm going to count the number of elements that are initially equal to each other before I do any reversal operations at all. And now I'm ready to begin looping over all of the intervals LR in this sort of clever method where I fix some element in the middle, and then I'm going to loop outwards in ever expanding intervals. So let's start this. We're going to sort of create our frequency array for the different counts that we see. And now we're going to loop over all positions I. And I here is the middle element that we're expanding outward from. And we want to think about sort of um, how far can I expand? Well, if I'm all the way to the left, so imagine I is equal to 0, then there aren't very many intervals where I is the middle element, right? In this case, there's just one interval where I is the middle element. And then the same thing's true at the very end of the array. So if we're looking at the very end of the array, so this would be position 8, I suppose. There's not very many values which contain position 8 as the middle element. It's just this one. But if we're in the middle of the array, then we can see that there's lots of values which contain the middle of the array as the middle element. In particular, there's this interval, there's this interval, there's this interval, there's this interval, and there's this interval. So the sort of two constraints on how many intervals have a value as the middle component is we have a constraint of how close you are to the left and how close you are to the right. So whichever is more constraining, so we're going to take the minimum of I plus 1 and n minus I. So this is how close am I to the rightmost element in the array, how close am I to the leftmost element in the array. Whichever those is closer, that's going to be the maximum number of times that this element I appears as the middle element of some interval of my array. So with that in mind, we're going to loop j, and j is going to be a marker of sort of how far I'm traveling out from my current value. And we're starting j at 0, but note that it is equivalent if you start j at 1, since it is pointless to reverse an element itself. But I think this just makes the problem a little bit easier to think about. So, and we're going to swap the values a minus j and a plus j. So the idea being that if I is the middle element, we're going to go j units to the left, j units to the right, and swap those two elements. And one option, you could actually swap those values in the array and then just reset the array every time. Um, or you could sort of just pretend to swap the elements and do the count manually. So what we can do is we can check if a at I minus j is equal to b at I minus j, then we are losing two equal elements. So we're going to decrease the count by 1. But then when I swap position I minus j to position I plus j, if those are equal, then I've regained a set of equal elements, right? So the element in this position ends up in this position. So if they're equal, I'm going to gain something. And then the same happens in reverse. If I plus j is equal to b at I plus j, I'm going to be losing that equal pair. But then if a of I plus j is equal to b of I minus j, I'm going to be gaining that equal pair. So I'm just going to shift my count up by these values, and then I'm going to record in my frequency array the current count. And this completes the problem for all intervals of odd length. And then I can continue on and repeat essentially the same logic, but for intervals of even length. So now instead of swapping the values of a at I minus j and I plus j, I'm going to be swapping the values at a I minus j and a I plus 1 plus j. So I'm going to be starting with the pairs I and I plus 1. Other than that, the code essentially stays the same. And then at the very end of our program, we simply print out the counts that we find along the way. And for people who are interested in the Python solution, again, here is the equivalent code in Python, where this handles all odd length arrays, this handles all even length arrays. But again, this is too slow to pass the test cases on the USACO server. So thank you guys so much for watching the videos. I hope they're helpful, and I will see you guys next time. Bye-bye.